Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are dealing with the chapter microwave transistors and tunnel diodes. The basic bipolar junction transistors working at the microwave applications or the microwave frequency range that we are discussing in this particular chapter. So very first of all, we started with the microwave bipolar junction transistor, the physical descriptions we are covered with, and the various microwave bipolar junction configurations for the transistor we have dealt with in the previous video. Let us have a practice of simple problem. So here for the problem, based on to the microwave bipolar transistor configurations, we are provided a problem statement. As per the problem statement, a silicon NPN bipolar transistor has the following parameters. The parameters are represented symbolically as capital I suffix C is equal to 6 milliampere, small h suffix Fe is equal to 120, capital T is equal to 300 degree Kelvin, W suffix B is equal to 10 raised to the power minus 8 centimeter square. We are asked to compute in the part A the mutual conductance that can be represented by Gm here. G will be having a suffix small m. In the part B, we are required to compute the input conductance G suffix B and the resistance capital R suffix I. In the part C, we require the value of the electron diffusion coefficient represented as capital D suffix small n. And lastly, we require the diffusion capacitance denoted as capital C suffix BE has been dashed here. So very first of all, let us identify what are the given details as per the problem statement, and then we can concentrate on finding the solutions for these parts A, B, C and D here. So now as per the problem statement, the first parameter is given to us. So I mentioned the given details. The first parameter has been represented as IC. The value is 6 milliamperes given to us, that can be represented as 6 into 10 raised to power minus 3 amperes. So this is actually the value of collector current. As the bipolar transistor, we know the three different regions we know. For the output case, we have the collector terminal to be collecting and producing this particular current here. So that is represented as capital I suffix C. So this is the given first parameter. After IC, now we are provided with the second parameter that has been represented as small h suffix Fe in capitals, and it has the value of 120. So as we know that the different transistor configurations, here the representation of h suffix Fe is nothing but the configuration of common emitter, and it is representing the current gain factor. So the current gain factor for the common emitter type of the transistor configuration is provided here with the value 120 here. The next parameter available with us is capital T is equal to 300 degree Kelvin. So this is nothing but the operating temperature. So I mention here operating temperature, whereas the last value is provided to us as per the problem statement that has been represented as capital W suffix B with the value 10 raised to power minus 8 centimeter square. So this is nothing but the cross sectional area. So these are the given parameters. We have been identified them. Now we get back to the problem statement. Now as per the problem statement, we focus our attention in the first part A here, we require the mutual conductance Gm is equal to what? Now for determination of the Gm, here we write the formulation. So Gm is nothing but mutual conductance, and it is computed as the ratio of the current, collector current IC, with the voltage denoted as V suffix T. Now the value of IC is already provided to us, and as you have gone through the understanding of the device configuration in the previous video, the value of Vt is to be assumed here. So it is a constant value, so we substitute both the values as known one. So here the numerator will become 6 into 10 raised to power minus 3 as the collector current, and the value of the voltage V suffix T is equal to 26 into 10 raised to power minus 3. So here 10 raised to power minus 3, 10 raised to power minus 3 from the numerator and the denominator will get cancelled, and finally the mutual conductance denoted by small g suffix m will be obtained as 0.23. It will be simply the division of 6 by 26. As this is the value of conductance, it should be measured in terms of mhos. Here I write MHO, or we can also write here to be the inverted omega sign. So this is the required answer for part A. I outline this particular answer. So now we are covered with the answer for part A. Now we require the computation of the input conductance denoted by G suffix B and the resistance value denoted by R suffix I. So R suffix I is equal to what and G suffix B is equal to what is the question to be solved in part B. So for part B, the input conductance denoted by G suffix B is basically the ratio of mutual conductance we have calculated as the answer of part A, G suffix M, to that of, here we have the gain factor with respect to the currents into the common emitter configuration provided to us in the given details, that is H suffix Fe. So this is the given value, and this value is just now computed into the previous answer here. So we substitute the previous answer into the numerator, so it becomes 0.23, and in the denominator the given value of this gain factor is nothing but 120. So by the division we obtain the resultant value of the conductance here, that it is 1.92 into 10 raised to power minus 3. So as this is the conductance, again the measurement unit is in terms of mhos, or can be symbolically denoted by like this. So this is the one answer as a part for part B. And now we require the input resistance also. The input resistance denoted by capital R suffix I is computed as, here we have R suffix I is equal to the constant value we have 521. In this particular case, as this is resistance, it should be measured in terms of ohms, or it can be represented as omega here. So here from the given details, the input conductance and the resistance input are also calculated here. We are well known with the relations of the conductance and the resistance, hence we have both the values computed here. Now we require the value of electron diffusion coefficient denoted as capital D suffix n. So here we start for part C. We require the electron diffusion coefficient, and this particular coefficient denoted as capital D suffix n is computed as, we require mu suffix n in multiplication to capital K into capital T divided by G here. This formulation can also be expressed in terms of the simpler form. We keep mu suffix n as it is in multiplication to the voltage denoted as capital V suffix capital T here. So now V suffix T we have already utilized in calculation of answer for part A. Mu suffix n we require, so it is the mobility value, and for the given configuration we have the constant value. That value we can substitute here. So we have it as 1600 in multiplication to the Vt value, that it is 26 into 10 raised to power minus 3. So finally the multiplication gives us the electron diffusion coefficient Dn computed as 41.6 in terms of centimeter square divided by seconds here. So this is the answer for part C here. So here we are finished with finding the solutions for part A, B and C. Now lastly we require the value of diffusion capacitance denoted like this. Now in the part D we require the value of capital C suffix BE dash here. So this is the diffusion capacitance, and it can be obtained by making the use of mutual conductance GM, the width value that is to be squared here, WB square, divided by twice into the electron diffusion coefficient Dn. So the value is computed as the answer A. This is provided into the problem statement, and this is also just now been computed into the previous section. So substituting these values we get the form of C suffix B dash is equal to 0.23 into, here we have 10 raised to power minus 8 divided by 2 into 41.6 here. So finally we obtained the answer as 2.76 into 10 raised to power minus 12. As this is the capacitance value, we must express it in terms of farads here, or we can absorb this multiplication so that we can write C suffix BE dash, that is the diffusion capacitance, is equal to 2.76 picofarad here. So I outline this particular answer. So with this answer we are covered with the computations of part A, B, C and D for this particular problem. By the next lecture we shall be addressing and dealing with the topic, the operating principles of microwave bipolar transistors. I hope you are getting the details of microwave engineering very well. For more information and knowledge like this, you can subscribe to Ekeeda channel. Thank you.